Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll talk about the motion of the planets and satellites. Before Newton developed his laws of gravitation, Johannes Kepler gave us 3 laws which describe the motion of planets in our solar system. We'll not prove these laws as that is not in your course, but we will go through these laws in a particular specific special significant case. Kepler's first law was that the planets move in elliptical orbits with the Sun at a focus. Now, you probably studied ellipses in your mathematics class. So an ellipse which has its center as the origin is something like this, and it has 2 foci. Right? If the major and minor axes are equal, then it's a circle and it has only one focus, which is the center. But otherwise it has 2 foci at the left and right of the center. So Kepler's first law stated that all planets move in elliptical orbits where the Sun is at one of the 2 foci. Kepler's second law was that the radius vector from the Sun to a planet sweeps equal areas in equal times. Now, this would be a very insignificant statement if we were talking about circular motion, because in that case this statement would simply translate to the speed of motion is constant. But we are not talking about circles. Actually, planets travel in ellipses. So let's look at this ellipse again. And if we take this to be the Sun, then this is the radius vector when the planet is at this point, and this is the radius vector when the planet is at this point. If we take a small instant after that, the planet might be here and the planet might be here. So these are 2 instances. What Johannes Kepler's second law says is that if these two time intervals are equal, let's say 2 days apart, then these 2 areas will have to be equal. Now, if this radius is much larger than this radius, that simply means that this has to be wider than this. Right? So this statement roughly translates to: the closer the planet is to the Sun, the faster it is moving. The farther away it is, the slower it is moving. Because when it is very near to the Sun and it needs to cover a certain amount of area, the radius is small, so it will have to move a larger amount. Kepler's third law says that the square of the time period is proportional to the cube of the semi-major axis. So this is the major axis and this is the minor axis. Semi-major axis is half of the major axis. It says that the square of the total time taken to complete one revolution is proportional to the cube of the semi-major axis. This particular law helped us in relating the motion of different planets to each other. The farther apart the planet is, the more the time period would be, and they're related as due to the third law. So these are 3 laws, and Kepler did not prove these 3 laws. He took a bunch of results that his predecessor Tycho Brahe had actually noted down from years of astronomical observations, and he was able to calculate these results based on those observations. He did not give any explanation for these. Newton was the first person to actually give an explanation for these in terms of the inverse square law, and that is why Newton is considered the founder of modern science. This was just stating of a bunch of facts which were concluded from observations. There was no explanation for these facts. Now let's look in detail about how planets move about the Sun, or about how satellites move about the planet. So we are talking about a very special case, and the case we will be talking about is, let's take this capital mass M to be the mass of the sun. Small mass M is the mass of the planet. I apologize for my drawing. This is supposed to be a circle. The simple case which we are talking about is, we will assume that all planets move in a circle about the sun. Let's take the radius of the circle to be a, and let's assume the planet is moving with the speed v. Right. So this is the center of the circle. This planet of small mass m is moving with the speed v. So this is a standard, very simple problem of circular motion. The force in this case on this particle will have a magnitude equal to gmm by a squared, but that has to also be equal to mv squared by a, because the radius is a in this case. If a particle is moving in a circle of radius a with a speed v, then it has to experience an acceleration towards the center of v squared by a, and hence a force towards the center equal to mv squared by a. So we can cancel m, we are just left with 1a. So this gives us the result, v is equal to root of gm by a. Right. So we have calculated the speed in terms of the distance from the center. If we wanted to do, we could calculate the kinetic energy of this object as well. We have assumed that the sun is at the center and the sun is stationary, so the kinetic energy will be half mv squared. That will be, v squared will be gm by a, so it will be gmm by 2a. The potential energy is something we already know previously, that is minus gmm by a. This is the potential energy of two particles which are kept at a distance a apart. Now this is again just a side note. This is another point where that Newton's result comes into play, that you can actually assume that a solid sphere is simply a particle kept at its center. If that were not true, then all these results would not be valid, because we are talking about 2-point particles. What is the total energy in this case? The total energy is the sum of the kinetic energy plus potential energy, and that is minus gmm by 2a, which is negative. Now this is an important point. What is the significance of negative energy? This you'll see again when you reach modern physics, or you might have seen in chemistry while studying Bohr's model. A negative energy means that the system is bound, it is not free to move. So this planet will forever, if nothing changes, move around this circle, and it will never be free to go away. It will be bound by the gravitational force of attraction. So if a system is bound, that means its total energy is negative, and if the system is free, that means its total energy is positive. Right. So let's try to see Kepler's 3 laws from this. The first law, that it is at the center with the sun at one of its focus. If we assume the orbit to be circular, then the center is the focus. So the first rule is true. The second, the radius vector from the sun to the planet sweeping equal areas in equal times, is also obviously true if the speed of the particle is constant and the radius of the circular motion is constant. The third result says that t square is proportional to a cube. So let's look at that. We know v is equal to root of gm by a. T will be the total time taken. That will be simply 2 pi a, that is the circumference, divided by the speed. The speed is root of gm by a. So this gives me the total time period is equal to 2 pi by root of gm a to the power 3 by 2, or it gives me t square is equal to 4 pi square by gm a cube. So this is a verification of Kepler's third law, which says that the square of the time period is proportional to the cube of the semi-major axis. So we've seen Kepler's 3 laws are indeed true if we assume that the planet moves in a circle about the center and the speed of the planet is constant. By the way, everything we've said is also valid, for example, if m was the mass of the earth and small m was the mass of the moon or a satellite going around the earth. A couple of other important points to note when we talk about planetary motion. The total energy can also be written as half mv squared minus gmm by a. Right. So in that case, now let's assume there is not technically a circular motion. This is also true for any object moving with the speed v near the surface of the earth. Right. And let's see when the total energy is negative. Total energy is negative when v squared is less than 2gm by a, or if v is less than root of 2gm by a. That means if v is greater than root of 2gm by a, the total energy will be positive. Total energy positive means the system is no longer bound, it is free to move. So in this case, if we stand at the surface of the earth, also the surface of the sun, and we throw a particle with a speed v which is greater than root 2gm by a, then that particle will never ever return back to the earth. Right, that particle will continue moving on forever away from the earth. And the minimum speed with which this happens is root of 2gm by a. And that is called the escape velocity for any planet. For the earth, if you put the mass of the earth and the radius of the earth in, it comes out to be around 11.6 kilometers per second. So anytime you throw an object upwards, it is bound to return back to you unless you throw it with a speed greater than 11.6 kilometers per second. If you throw it with a speed less than 11.6 kilometers per second, and if you take the earth and that object to be a complete system, it will eventually come back. Because the total energy is negative, it is a bound system. But if you throw it with a speed v such that the total energy becomes positive, then it will never come back. And this is the formula for the escape speed of the earth. Another important result, if for certain planetary objects this escape speed, by the way, for some reason it is referred to as both escape speed and escape velocity, though technically it should be called escape speed because we are talking about the magnitude only. If this is root 2gm by a, if it turns out to be greater than c, which is the speed of light, in that case even light will not be able to escape from that object. This is true for objects which are called black holes. Actually, Einstein's changes to the gravitational theory actually refine it a little bit, but for the sake of your understanding, this is pretty much what it is. If the mass of an object continues to remain the same, but we condense it such that its radius keeps on decreasing, the escape speed will keep on increasing until eventually there will be a point when the escape speed will be greater than the speed of light, and we know that no material object can have a speed greater than the speed of light. So in that case, not even light will be able to escape from that planetary object, and that is called a black hole. One last point which you should know is, if you are talking about geostationary satellites are satellites which move in the equatorial plane of the earth like so, but if you are standing at a particular point on the earth, they look to you to be stationary. So if you need to see an object to be stationary, that means that object has to be revolving around the earth. If that object is literally stationary, then you would see it to move just like you see the sun to move, because relatively the earth is moving. But if that object rotates with exactly the same frequency as the earth, that is once every 24 hours, then every person will see that object to be fixed at a particular point in the sky. So for geostationary satellites, the time period should be 24 hours. Now if you put the values of time period in Kepler's third law, you will see that A will come out to be 4.2 into 10 to the power 4 kilometers. So this is the distance from the center of the earth. The distance from the surface of the earth will come out to be 3.6 into 10 to the power 4 kilometers, because the radius of the earth is approximately 6400 kilometers. That means all geostationary satellites are at this height above the earth's surface. And the height determines the speed. If you want the height to be greater, the speed has to be greater. If you want the height to be smaller, the speed has to be smaller. This completes our unit on gravitation. Thank you.